Hello everybody. Tonight I'd like to talk to you about oil and natural gas. And if you think about it, petroleum products play an amazingly large role in our life and in all of modern life. At a personal level, petroleum produces electricity, it powers our cars, it heats and cools our homes, um, and so many of the products we use contain oil-based raw materials. It powers modern farming, and petrochemical products are used routinely in the food that we eat. So, at a very personal level, oil has become exceedingly important in our life. Our industries are organized around oil. Oil powers factories. It's the raw material for many products. It's the basis of much of our organic chemical industry, and it powers the transport of goods. And it is now central to our economy. It is so central, in fact, that a price change in oil has repercussions throughout the economy. That's perhaps not a good thing, but at this point, it's a fact. Now, oil and natural gas currently provide about 62% of the U.S.'s energy as of 2009. At the same time, they provided about 58% of the world's energy. It wasn't always this way. Historically, they were much less important. But by 1930, they were the leading fuels, mainly because they were cleaner, they were more versatile, and they were easier to transport than coal, which had been used to power the first 100 years of the Industrial Revolution. If we just look at the U.S. for a moment, we will see that oil consumption has been pretty steady over the last 15 or so years, and that our domestic supply does not match that in the last 15 or 20 years. The demand for oil in the U.S. rose sharply during the 1960s due to the advent of car culture, due to the fact that it became common for everybody to own a car. And indeed, I remember my parents not owning a car for many years, and then the excitement of us getting one. As I said earlier, consumption in the U.S. far exceeds domestic production, and so we have to import oil, and we're dependent on other people, and that can lead to a loss of foreign exchange. So our need for oil becomes a political football. Peak domestic production in the United States occurred about 1970, and the domestic supply has been fluctuating ever since then, although because of fracking, you see this uptick in the supply of natural gas that occurred here in the 2000s. Currently, we use about 20 million barrels per day, which is about 20 to 25% of the world's production. So we use a fifth to a quarter of the world's production. The U.S. uses 7.3 billion barrels of oil per year. Petroleum, or crude oil, which is what comes out of the ground, must be processed, a process we call refining, in order to turn it into products that we can use. Crude oil contains numerous hydrocarbons, which, if you remember your chemistry, you might remember what they are. Energy-rich, carbon-based compounds. And we need to separate them, and in order to separate them, we heat them slowly and collect them as they volatilize, as they turn from a liquid into a gas form. We collect them in a distillation unit or a condensation column. As you can see in the diagram on the left, the first thing that comes off are gases, like natural gas. And then after that, gasoline comes off, and then aviation fuel, and then kerosene, heating oil, and diesel oil are next, and then lubricants. And finally, what's left over at the end is asphalt, which we use for paving roads. And you can imagine that this is a process that has to be done very carefully because so many of these compounds are explosive if they're combined with oxygen. So this is a process that cannot be done in the living room, let's say. In contrast, natural gas contains far fewer hydrocarbons because it doesn't contain liquid. It mainly contains methane, natural gas, propane, which you've probably heard of, and butane, which you've probably heard of. Butane is used in cigarette lighters, for example, and propane is often used in places that aren't served by natural gas. So natural gas, as it comes out of the well, is often separated as well into these three components: methane, propane, and butane. Propane and butane, when they're separated, are often compressed into liquids, which are known as LPG, liquefied petroleum gas. LPG can be transported as a liquid in a tank, and then the tank can be set up so that when you turn it on, the gas will come out. And this is what your grill uses, and it's also used for heating and cooking in rural areas. You'll have a large tank outside the house that the gas company will fill up periodically. Methane is used for heat to generate electricity in power plants. It can be used as a fuel for vehicles and transportation, and in urban areas for cooking. But the big thing about methane is it must have a pipeline distribution network. And so only large cities can use a pipeline distribution network. And thus we see methane mainly used in large cities. Natural gas has the advantage of being the cleanest fossil fuels. And it's clean because it emits fewer hydrocarbons and less carbon monoxide, fewer particulates or soot, 90% fewer toxic emissions, and that's the particulates in particular that are included in that. The problem with natural gas is it still emits carbon into the atmosphere. However, it emits it at a relatively lower rate than oil and coal. So per unit of energy, you have less carbon being put into the atmosphere. The drawbacks of natural gas is the deposits are often far from where the methane can be used. Remember, it needs to be used in places where there's a distribution network of pipes. And shipping it is expensive because it's a gas and has a low density, so it has to be compressed. And to be compressed into what's called LNG, which is liquefied natural gas, not to be confused with LPG, which is propane and butane, liquefied petroleum gas. Methane compressed is called LNG, liquefied natural gas, and transported on refrigerator ships, which require very low temperatures, as low as 105 degrees below 0 centigrade. And then it must be brought to regasification plants, which are shunned by local communities because they risk explosion, although admittedly that risk is very low. And then they're shipped by pipes to where the natural gas is used. And so many places, as I said earlier, are not served by natural gas. I want to say a word about how oil and natural gas are found. Companies have realized that the easiest way to find natural gas is to look for certain geological formations that indicate the possibility of oil and natural gas occurring there. Oil and natural gas, when they're formed, being of low density, float upward underground until they hit an impermeable rock layer. So petroleum deposits are found by looking for these dome-like structures underground. And thus petroleum companies have hired geologists to virtually map the entire planet and what the geology looks like in the first several miles below the surface. So we have really excellent maps of the geology of the Earth. Oil and natural gas are often associated with salt domes, because don't forget when we talked about how petroleum is formed, it's formed from the remnants of marine organisms. And so the salt domes are areas where a huge amount of salt water evaporated at one point, old ocean bottoms that have been raised to the top and where ocean water has evaporated over time. So that's how it's looked for. Now, we talked about this earlier, but I just want to remind you, oil reserves are unevenly distributed. More than half of the remaining oil is located in the Middle East. Same with natural gas, unevenly distributed globally. More than half is located in Russia and Iran. The United States still has a good amount, particularly in fracking fields, which we'll talk about in the next talk tomorrow. One big question is, how long will supplies last? And what you see in the picture here is a gas line when there was gas rationing during the 1973 oil crisis in the United States. So the Earth may have already reached peak oil production. Some people believe it's already happened. The most optimistic prediction states that the peak will occur in 2035. At any rate, we're in the time of peak oil right now, and after this time, it will be decreasing within the next 2 decades. Now, in 2013, British Petroleum's annual report published a statement that said that the known reserves of oil would last 53.3 years at current rates of consumption. And we know that consumption of petroleum has gone up since then. Now, this is a very controversial figure, and many people rush to say, oh, British Petroleum was wrong. But the fact that it was British Petroleum saying it meant that a lot of people took it seriously. And it also brought to light that we are going to have to find alternatives to fossil fuels relatively soon. The actual duration of the supply depends on numerous factors. One is locating more deposits and different types of resources from which petroleum can be extracted, particularly these low-grade petroleum products from which we can create synthetic fuels. And that I will also talk about in tomorrow's talk. It also depends on the ability to develop better extraction technologies in the future. It depends on changes in global consumption rate. Will they continue to go up as they have been, or will we finally start to decrease our consumption, in which case the oil supply will last longer? As oil becomes scarce, prices will rise and use will decrease, so that will prolong its life. Higher prices, however, will allow reserves that are more difficult to extract to become profitable, so that will tend to depress the price. So as you can see, this is a very complex prediction to make, and nobody's really sure how long it's going to last. But most people believe that decreased production will become a problem in this century. I'll let you get your head around that. So let's look at the environmental impacts of oil and natural gas, many of which you could guess. And if you want to, turn off the film for a second, take a guess as to what they are. Okay, so let's start to go through them. The big one, of course, is climate change. We already know that. Each gallon of gasoline that we burn in our cars releases 9 kilograms of carbon dioxide into the atmosphere. Natural gas is cleaner, but it still leads to climate change. In addition to climate change, which is the biggie right now, there is acid deposition. The high compression and high temperature engines in which petroleum products are burned produces nitrogen oxides. Many of the petroleum products produce sulfur, and when they're burned, they produce sulfur oxides, and both of these create acidic particles in the atmosphere, and they fall back to the earth as acid rain or as acidic dust particles, which acidify local ecosystems and change them. There's the disturbance to land and habitat that occurs wherever oil drilling and fracking are done. And there's leakage into the environment, especially spills, and that's especially problematic in aquatic ecosystems. And I'm going to take a look now at the two biggest U.S. spills, the spill of the Exxon Valdez in Alaska in 1989 and the spill from the Deepwater Horizon drilling platform in the Gulf of Mexico in 2010. So before we get to those spills, let's just talk for a second about what happens when oil spills and why it is a problem. First of all, much of the oil floats if it's on water because it's less dense than water. And so it is dispersed by wind and currents fairly quickly. Some of it evaporates and some of it sinks to the bottom. So now you have lots of different problems going on there. The surface oil can be cleaned up to some extent, whereas the bottom oil cannot be, and the stuff that gets into the atmosphere cannot be cleaned up either. So the surface oil can be cleaned up to some extent, and I'll show you some pictures of that. First of all, a really good solution to it is to set it on fire if you can. So if the oil is thick enough on the water, just light it on fire. And even though that has a climate change implication, it's a good way to get rid of the oil and cause it to not adversely affect the ecosystem and wildlife. It then would be contained by booms, and then you have small worker boats that come around and try to scoop up the oil. The problem with this, it only works when the ocean is calm. If the ocean gets rough, the boom will not contain the ocean. And by a boom, I mean a floating barrier that surrounds the oil. And so if the ocean is rough, the oil gets around and under and over the boom, and it disperses much more quickly, and so it can't be cleaned up. Sometimes what happens is you use surfactants, which are like dish soap, and they break it up into small pieces. That allows the oil not to accumulate in any one place, and that is a dilution solution. And you may have heard the expression, we haven't used it in this course yet, the solution to pollution is dilution. And that is an old-fashioned idea that if you just make something dilute enough, it probably can't hurt you. And we'll talk about when that's not true, or maybe I should say how that's not true when we get to the environmental health unit. So the effects of a spill are destruction of wildlife. Some animals that get caught in the spill can be recovered with intense human effort, but most perish. Even many of the ones that are cleaned up by volunteers perish. Next, we have destruction of ecosystems. Ecosystems, primary producers, habitat will get covered in oil, and it cannot be used by wildlife. It either kills wildlife when it comes in contact with it, or wildlife just leaves the area. Often takes years, decades to recover, and oil can remain hidden. It's not being degraded by anything, so it can remain hidden for decades and perhaps longer. Fisheries are often shut down or suffer reduced harvests immediately after a spill. And tourism is often curtailed. And this was something that happened after the Deepwater Horizon Gulf of Mexico disaster. Oil spills produce especially graphic images of pollution and wildlife that is in trouble. And I'm going to show you an image or two of that. And thus, they are a public relations nightmare for corporations because they have a big effect on the public and maybe even a disproportionate effect in terms of the damage they do compared to how the public reacts. For example, the public should probably be far more upset right now about climate change and the effect that that's going to have on wildlife. But one good oil spill will produce a tremendous amount of public support for reining in the oil industry. Historically, the years following a major oil accident have been times when major legislation regulating oil companies has been passed. And so one has to strike when the iron is hot if they want to get environmental legislation passed. And we're going to see this several times over the course of the year. So let's look at the 1989 Exxon Valdez spill. The Exxon Valdez was a supertanker. These are humongous boats. I'll show you a picture of it in a second. It hit a reef and spilled 260,000 barrels of crude oil because the captain was intoxicated at the time. It was the largest oil spill in U.S. history, 260,000 barrels, and I believe a barrel is about 55 gallons. The estimate is that about 30,000 seabirds perished initially, and at least 3,500 sea otters, which had been endangered in the decades prior to that, were killed immediately by this spill. In subsequent years, populations of other animals such as orcas, killer whales, sea lions, and salmon decreased for several years after that. The fishing season in that area was lost for the year. The cleanup was declared complete some years later, but problems persisted, were still occurring 10 to 20 years after the original spill. The upside of the spill was the Oil Pollution Act of 1990 had several important impacts. First, it established liability. Up until that time, oil companies weren't responsible if they spilled oil. It's hard to believe, isn't it? It's hard to believe that oil companies could create a disaster and walk away from it, but it was true. By 2015, all the super tankers were required to be double-hulled ships so that if they ran into a reef, oil wouldn't spill. And the Oil Pollution Act also established a cleanup fund that would be used in the case of future spills. So let's look at the Valdez. There it is. Look at that. It's off the coast of Alaska. An incredibly large ship, most of the hull being filled with oil. Here's a western grebe after it had swum through the slick. That bird is moribund, will not be able to survive even if human beings rescue it. It will have probably ingested so much oil already that even if you could clean its feathers up, which you can using a lot of the detergent and human effort, the oil will not allow it to digest food. So here is a picture of the oil spill and one of these boats that is trying to clear it up. And this is a boom, and here's a little skiff that is surrounding oil that can be skimmed by this boat and taken off the surface of the water. But you can see this really looks like a hopeless task here. And of course, it's going to be an imperfect task. And there are going to be little bits like this, which are going to float off to sea. So the Valdez picked up its cargo in the Alaskan town of Valdez. And that oil comes from the Arctic oil field on the north slope of Alaska. At Prudhoe Bay, it is put into the Alaskan pipeline and then transported to Valdez, where it's put on tankers and then is taken to refineries around the world. And it was somewhere in Prince William Sound here that the Valdez hit a reef. Let's look at the Deepwater Horizon spill. On the 22nd of April in 2010, the Deepwater Horizon had a blowout. The Deepwater Horizon was a drilling platform. These things are amazingly expensive pieces of technology that float on the water and have a series of motors that keep them in place above the oil well. And then the oil well is some 4,000 to 6,000 feet below the surface on the floor of the Gulf of Mexico. Well, the natural gas in this exploded and killed 12 people, caused a tremendous fire, and eventually the rig collapsed. It became detached from the wellhead 6,000 feet below. No fear, there's safety equipment on each wellhead that is designed to shut in the case of an emergency like this, and it didn't work. It failed. So it took something like 87 days for the well to be capped, and it really was a marvel of technology that people were able to get an unmanned submarine down there and carry a piece of equipment that was able to shut the wellhead. But in that amount of time, 4.9 million barrels, or about 210 million gallons of crude oil, flowed into the Gulf of Mexico. This was 19 times bigger than the Valdez, and the spill covered an area of 75,000 kilometers, which I'll show you in a second. Here are some photographs from the Deepwater Horizon. Here's what it looks like before it exploded. And you can see there are these giant pontoons under. You can't see them, but giant pontoons, each with a motor that keeps this thing in place. And then the oil and gas come up here, and it's collected up here, and then it's offloaded onto ships and taken to shore. And here's what it looked like when it exploded. And you can see there were tons, 6 firefighting boats, 5 spraying water on it. And they could not do much to put it out. That whole thing disintegrated, melted, and fell into the ocean, and then the wellhead leaked. Here is the extent of the Deepwater Horizon spill. It is truly horrific. You can see it went all the way over from Florida to Gulfport, Mississippi, to Louisiana. So that's it for today's talk on oil and gas. I hope that you now understand some aspects of oil and gas production, how oil and gas are used, and the environmental issues that arise from using these products. Until next time, study hard.